Welcome, MagLab, to the first 2023 presentation of Magx, which are across the entire MagLab general lectures to engage people across our MagLab. I'm delighted to say that our first speaker of 2023 is Lucia Steinke, and she will be introduced with the discussion leader of Mark Mizell, both from the High B over T facility. Take it, Mark.
Okay, thank you, Laura. Good afternoon, everyone. It's a pleasure for me to introduce Dr. Lucia Steinke, who's an associate scientist in the Department of Physics here at the University of Florida. Lucia arrived in October 2019 after a department search committee recommended her to the faculty, which voted on her appointment. Consequently, when she recruited a graduate student who needed to form a PhD supervisory committee, the department met and voted again, and the Dean of the College of Liberal Arts and Sciences and the Dean of the Graduate School approved her appointment to the graduate faculty. Lucia now chairs Alex Donald's PhD committee. Lucia received her PhD at the Technical University in Munich, and then she spent several years as a postdoc at the Max Planck Institute for Chemical Physics of Solids in Dresden, and Brookhaven National Lab and Stony Brook University on Long Island, New York, and then Texas A&M University, where she was promoted to associate research scientist before coming to UF as an associate scientist. Lucia has amassed a wide range of expertise on adiabatic demagnetization cooling techniques and related measuring probes for the study of quantum matter in all flavors and extreme environments. Lucia brings a creative and gregarious spark to our MagLab team here at the University of Florida. And today she was going to tell us about one aspect of her work. I ask that you remain muted and raise your hand to ask questions in about 20 minutes from now. Lucia, regale us.
Okay, well, thank you very much. I hope you can all see my screen right now. So, and thanks for the really kind introduction. So I'm Lucia Steinke, I'm an associate scientist at UF, and I'm managing the MagLab High B over T facility. Today I'll talk about measuring thermal properties of quantum materials at extremely low temperatures and show you how important it is to make such probes available to our users. So I'll start with a little overview over our facility and what we're doing for the MagLab. And then I will talk about a particular puzzle involving unconventional superconductors and how experiments I did at a lab with similar capabilities helped solve part of that puzzle, and how that inspired me to develop better thermometers for experiments like that to use in our facility. So our specialty is really to provide users with two extreme experimental conditions combined: high fields in combination with ultra low temperature of below 1 millikelvin. That's about 10 times colder than the coldest cryostats in the other MagLab facilities. So how do we get our cryostats that cold? We employ a technique called nuclear demagnetization cooling. That starts with a material such as copper that has nuclear magnetic moments. That's what we call our nuclear cooling stage. We apply a strong magnetic field to align the nuclear moments that removes entropy, which equals heat from the nuclear system that gets dumped into the copper conduction electrons, and subsequently removed in a pre-cooled step by a closed cycle refrigerator. And now we're ready to completely thermally isolate the nuclear cooling stage, that's the adiabatic step, and slowly turn off the magnetic field. That allows the nuclear moments to become disordered again and soak up heat from the conduction electrons in the process. Using this technique, we can reach ultra low temperatures of 1 millikelvin and below and stay at these temperatures for weeks if needed. And now our specialty is that we combine these ultra low temperatures with high magnetic fields up to 16.5 Tesla. This is what that looks like on a chalkboard. So let me show you what that looks like in real life. Here's an image gallery showing our microkelvin lab of the High B over T facility. Apart from Mark and myself, we have two more permanent staff scientists working there. Xiao Huan is mostly responsible for the Bay 2 cryostat. Rasul Gazizulin has recently set up a brand new cryostat in Bay 1. And I'm mostly working on Bay 3, which you see out in the open here. So that's our nuclear cooling stage where we apply one magnetic field. And then at the bottom of a long cold finger is where you find our sample. And this is where we have a second magnet for the experiment. So these setups with two stacked magnets require a lot of space and a lot of liquid helium to stay cool. And because of that, UF cryogenics is actually really, really good at recycling helium. And as a fun fact, we recycle the equivalent of about 0.01% of the worldwide helium consumption every year, which I think is a pretty impressive number that we did just on a worldwide scale. And now, what kind of user needs a massive facility like that? So it is often people who are scientists who are studying quantum mechanical properties of materials at very low temperatures to begin with. And one example is superconductors. And now I'll show you an example from my own work where a similar facility was used to study an unconventional superconductor. Now, to give you a little bit of context for that, let's start with superconductors in general. So here's a list of some superconductors that are known by now, listed by their critical temperature and the year in which they were discovered. And for the first 75 years of scientists studying superconductors, actually most of the, or all of the known superconductors were non-magnetic metals. It was found that if you put even the tiniest amount of magnetic impurities into a superconductor, that would destroy the superconductivity. So it was believed that magnetism and superconductivity were mutually exclusive. And then it came as a big surprise when in 1979, Frank Steglich discovered superconductivity in cerium copper to silicon 2, which is a paramagnet. It has magnetism arising from the unpaired from the unpaired f electron in cerium, but yet it shows a clear superconducting transition seen in the resistivity dropping to 0 at 0.6 Kelvin. And that was really surprising because it's a magnet, and because cerium copper to silicon 2 was so different from all the known superconductors that at the time, it was deemed the first unconventional superconductors. Now, since we have discovered quite a few more, some of them are of the conventional type, like the early metals here. So those are the green dots. And we also have a pretty good understanding of how they work and what makes them superconduct. And we could even predict these really high temperature ones successfully. But then there's a whole zoo of other superconductors that are of the unconventional type that we don't understand so well, including the high TC ones. We don't really have a very good theory yet of what makes the transition temperatures in these things really high. But we can look for some logical clues for what do they all have in common. And one thing that has been observed is that superconductivity in such materials appears to be related to quantum critical points. So I'm giving you a little bit more background. What is a quantum critical point? It has to do with phase transitions. Everybody's familiar with this phase transition of ice melting or freezing at the critical point. That's the freezing point. But temperature is not the only thing that can drive a phase transition. There can also be other control parameters, such as pressure or magnetic field. Those are called non-thermal control parameters, and in combination with temperature, they allow us to draw a phase diagram. Now, the example that I'm considering here is a magnetic material that orders antiferromagnetically, so with anti-parallel moments below a critical temperature. If my control parameter allows me to continuously suppress that phase transition until it happens at absolute 0, this is when I've reached a quantum critical point. Now, there's a lot of fun stuff happening at quantum critical points like this. And one thing that you may find there is an unconventional superconducting phase. Now, does this hold true for the first unconventional superconductor? Yes, it does. So here's a phase diagram that was measured for cerium copper to silicon 2. Now, the non-thermal control parameter is a combination of hydrostatic pressure and chemical pressure. So that was achieved by germanium substitution. And I don't want you to get lost in the details of this phase diagram. There's quite a few superconducting phases here, but I want you to pay attention to this one. So there's the superconducting dome that occurs right where an antiferromagnetic phase is suppressed to 0. So superconductivity at quantum critical points appears to be true in the first unconventional superconductor discovered by Frank Steglich. But it was also the Steglich group who found that in the same class of materials, there was an apparent outlier, some oddity. And that was ytterbium rhodium to silicon 2. What is odd here is that it's actually very similar to the original cerium copper to silicon 2. It has the same crystal structure, except ytterbium replaced for cerium, and rhodium for copper. It's also magnetically quite similar. It just has one hole in the F shell instead of one electron. But its phase diagram, now shown as temperature versus magnetic field, shows an antiferromagnetic phase with a quantum critical point and some beautiful quantum critical behavior, yet no superconductor down to 10 millikelvin. That intrigued the Steinke group to literally get to the bottom of this puzzle. Why ytterbium rhodium 2 silicon 2 isn't superconducting, and to push the boundary of this phase diagram below 10 millikelvin. For that, they collaborated with the Walter Meissner Institute, where they had a microkelvin facility somewhat similar to ours, and at first measured the magnetic properties now to much lower temperatures. They could verify in the DC magnetization versus temperature that there was the antiferromagnetic phase transition at 70 millikelvin. But then as they cooled the samples further, they saw a second very pronounced peak that indicates that there is another transition happening. And we were speculating that this might be a superconductor. So when I joined Frank Schäblich's group as a postdoc, my first job was to try to find out if it was a superconductor. Now, one of the obvious things you think one might do is measure resistivity, but we decided to not do that as the first step because that's actually extremely hard at these temperatures and when the sample is a good metal. So instead, we decided to do another magnetic measurement. So instead of magnetization in a static magnetic field, we measured AC susceptibility in an alternating magnetic field. And that also shows a signature that is characteristic of a superconductor, and that is a drop towards reduced magnetism. In a textbook superconductor, that would go all the way negative to basically perfect diamagnetism. In this case, it doesn't go all the way negative, but it's not completely surprising considering the sample is magnetic. So that's a good indication that we could have a superconductor here. Another experimental probe that we can employ to find out about this is measuring specific heat. That could give us an idea of how many states are involved in this phase transition. So we also did that in this temperature range. And the basic idea to measure specific heat, so the response to heat of the sample is very simple. You apply a heat pulse, and then you watch the thermal relaxation, and from the time constant, you can extract a specific heat. But one thing that you already see in this setup is we had to play a few extra tricks because things aren't quite as simple at ultra low temperatures. They're basically two issues here. The first is heat leaks. Heat leaks are everywhere if you're working at 2 millikelvin. And one particularly difficult source for a heat leak was our function generator that was used to apply heat pulses to a heater. And if we had this directly connected, it was putting so much heat into our sample, even if we are not applying a heat pulse, that the sample was just staying way too warm and we didn't see the transition. The solution to that was to electrically completely decouple the circuit for the function generator from the circuit providing the heater power via light, via using an optocoupler. And now it's a battery that's heating the sample. That trick allowed us to actually get the sample cold. Now, the second challenge was how to measure its temperature, because there aren't really that many good thermometers that work under these conditions at super low temperatures for such a tiny sample. See, this is only 2 millimeters. In this case, our workaround was to use the sample itself, because we knew that the sample had a very strongly temperature dependent magnetization, and we still had it inside our squid magnetometer. So we decided to just look at the magnetic response of the sample. And that's what that looked like when you measured it. So what you see here is magnetization versus temperature, which is slowly varying over time because we apply constant heat to our cold reservoir of the nuclear stage. And then in regular intervals of about an hour, we apply short heat pulses to the sample that just briefly change its temperature a bit more. And then we watch the thermal relaxation. And now importantly, this is not measuring temperature, this is measuring magnetization. But because we're looking at the magnetic response to a thermal excitation, the time constant is thermal in nature. And from this time constant, using the thermal resistivity of a weak link to our nuclear stage. And so using that, we can extract the specific heat. And this is the specific heat that we measured using this technique. So this is not plotted versus temperature. And you see we can have a very pronounced peak at around 2 millikelvin, which is where the transition occurred. Now I've plotted this as specific heat divided by temperature. That's convenient because now I can calculate what entropy is involved, how many states are involved in this phase transition by calculating the area under the curve. So the entropy here is 2.02 joule per Kelvin and more. To make that a more meaningful number, let's try to benchmark it with something. One benchmark I could think of is well, comparing it to the superconducting transition in cerium copper to silicon 2. And there I looked at the original data published by Frank Steglich in 1979. And you see that the entropy under these two superconducting peaks here in two different samples is about 10 times lower than what I measure in ytterbium rhodium to silicon 2. So in other words, this specific heat is huge. And it is so large that we could not explain this transition with anything only involving conduction electrons. So it couldn't just be a superconducting transition. And it turns out what happens is, in addition to there being an antiferromagnetic phase, there is another type of magnetic order happening, and that involves nuclear moments, same moments that we use for cooling, on the ytterbium side. So there are ytterbium isotopes that have nuclear moments, and when they order, they compete with the antiferromagnetic phase and weaken it enough that that allows for superconductivity. So in other words, the nuclear moments are actually acting like another tuning parameter, pushing the system closer to a quantum critical point. And with all of that data combined, we are finally able to complete the phase diagram of ytterbium rhodium to silicon 2 at ultra low temperatures. And found that, so there is, in addition to superconductivity, there is a nuclear ordered phase here that is clearly indicated by the entropy. We could also show that the superconductivity actually does occur at the quantum critical point. So the superconductivity extended all the way to like 60 millitesla. The difficulty here is because it's a magnetic tuning parameter, is the field required to reach the quantum critical point was similar to the field, to the critical field of the superconductor. So we are suppressing both at the same time. But this really showed that superconductivity near quantum critical point is true even for the seeming outlier ytterbium rhodium to silicon 2. Eventually, it was also shown that resistivity went to 0. So Silke Paschman's group went through the trouble of actually measuring the resistivity. So all of this together showed us it is indeed a superconductor. But this is a lot of trouble for an international group of scientists to go through over decades to prove that one material is superconducting below 2 millikelvin or below 10 millikelvin. So why is it important? It's important because it was an outlier. It is important to help us understand the big picture of what makes all the unconventional superconductors work. And now knowing that this is a superconductor too, just changes the logic with how we approach it. And instead of thinking what makes ytterbium rhodium to silicon 2 different from all the unconventional superconductors, now we have to think about what's actually making it similar. What do they have in common? And I hope this also gives you an idea why it's really important to give scientists access to facilities like ours, where measurements under such extreme conditions are possible. Now, this project also inspired me to tackle one particular challenge after seeing how useful these thermal measurements were and how difficult it is to find good thermometers. I decided to invent one. And turns out that the solution for that is found inside quartz watches. So quartz watches, so the oscillators inside quartz watches are little tuning forks that have been used for a long time in ultra low temperature physics to measure the temperature of helium-3 baths. And I figured out that you could use the same technique to even measure the temperature of a small sample, because the tuning fork probes the viscosity of helium-3 liquid. And that's an intrinsic property of the liquid, meaning it doesn't depend on how much liquid is around the tuning fork. And that allows me to make this bath really small and then make completely self-contained thermometers with helium-3 inside that are of similar size of the samples I want to measure. So now I can use them as probes for the samples. And the viscosity of the helium-3 inside is strongly temperature dependent. It gets more viscous as it gets colder. So then if you look at the tuning fork response versus frequency, you see a very damp resonance. And at higher temperature, you have a sharper resonance. So looking at the width of this resonance, we can use that as a measure of temperature. Now let's put these prototypes that we built to the test to see if they're actually good to measure temperature. So now here is the resonance width over temperature for both a tuning fork inside a larger helium-3 volume. And this is one of our first thermometer prototypes. This was actually one that was built by my grad student, Alex Donald. I think he was the first one to get one of these to work. And he also did this measurement. And what this shows is that this is a really good thermometer, and that I can measure temperature from the resonance width over more than 3 decades, over more than 3 orders of magnitude. And I have an extremely predictable 1/T temperature dependence. So I might not even have to calibrate it. Another important characteristic to look at is not only how well can we measure temperature, but also how small of a difference in temperature can we resolve. So this is shown here. If you zoom in on part of this curve and just really look at the noise around the curve and project that onto the temperature axis, it gives you an idea of the resolution of this thermometer. And at present, I estimate that in this regime around 2.5 millikelvin, our resolution is around 50 microkelvin, which corresponds to roughly a 2% error. And if I compare that to commercially available resistor thermometers, which might do this job at higher temperature, see, it's comparable if we are at low field. But if we apply a sizable magnetic field, like 14 Tesla, the resolution of my thermometer stays the same and this one doubles. So my thermometers actually also work better in magnetic fields. So this is really all I wanted from them. I now hope that we can put these to use in user experiments in the future. So to summarize, I hope I've given you an idea of what we do at our facility and why having a user facility like this one is really important. I've shown you that we performed experiments in a similar facility to show that ytterbium rhodium-2 silicon-2 is a superconductor after all. And that inspired me to develop new miniature thermometers based on quartz watches. And I also showed you that you can use a quartz watch as a thermometer. Well, I haven't quite shown you that, but I've done the test. So I've done it with this watch. All you really have to do is you have to drill a hole in the can that contains the tuning fork. Once you've done that, you've exposed it to a viscous medium, that is air, and that slows down the watch at room temperature, but the air gets more viscous in the freezer, and it slows it down even more. So you lose over 24 hours in this time lapse, you lose an extra 2 seconds in the freezer. So yeah, it works. You can use a quartz watch as a thermometer. I also have to admit that I destroyed 3 other watches in the process. I had to film for 2 days straight, and I couldn't open my freezer for a day and access my pineapple bits, but it was really satisfying to see this work. Okay, so with that, thank you very much.
Awesome. Thank you. Thank you very much, Lucia. That's bravo. And yeah, I'm happy to hear. I'm glad you could get your frozen pineapple bits. Please, at this time, raise your hand. I'll recognize you to ask a question. Ryan, please, your question, please. Okay. Others, please raise your hand if you want to.
Hi, Lucia. That's a awesome talk. Really enjoyed it. And
thank you.
I've paid attention to the ytterbium rhodium-2 silicon-2 work, which I think is just really awesome. Anyways, is there an understanding at this point for why the TC for the ytterbium one is so low?
I don't think we have an understanding why it is so low, because I mean it appears to need the help from the nuclear moments. But that could really be that it just needs extra weakening of the antiferromagnetic phase. But if it's truly intimately linked to the presence of nuclear moments, then you have to be at a temperature where those want to order, and that would always be fairly low. What was interesting though was that Silke Paschen's group in the work that she did to measure the resistivity, she also tested the influence of nuclear moments. And so she created samples that didn't have any nuclear spins in them by just choosing the right isotope. And that further weakens the superconductivity, but it doesn't make it completely disappear. So it's not like superconductivity is playing an absolutely critical role there.
I see. Okay. That's really interesting. Thank you.
Yeah.
You're welcome. Other questions, please? Yes, Laura, I see your physical hand being waved. Yes, you have unmute for you to ask your question, please.
Yeah, I was wondering, it's really fascinating with this material, and there's so many classes of unconventional superconductors. Where is this going to lead you next? What other kind of unconventional superconductors do you want to look for to see if they're outliers or part of the same family? Well, because they're different families, so yeah.
Well, there's really two things. I mean, one thing I think is what's really important with, let's say, the capabilities we have in our labs is to actually even look at similar things as ytterbium, rhodium-2, silicon-2, where the superconductivity is either just happening or not happening, because we just get extra information on these systems that we can't get from things that have ordering temperature of like 80 Kelvin. It's also easier to see the quantum criticality. But I'd also like to just really test this, is there really a fundamental limit to superconductivity? Because so far, we don't know. We haven't really tested so many superconductors to extremely low temperatures. So, I mean, this one is a very low transition temperature, but bismuth is even lower, for example. It's like half a millikelvin.
And there's some, I think it doesn't serum copper 6 still not have a TC that's measured, and which is an outlier. That might be an interesting direction to go.
Yes. And especially, well, I need samples to go on these thermometers now. So yes.
Yeah, thank you, Laura. So you go ahead, Ryan, please.
We're happy to send samples. That's all I wanted to say. Anytime.
Sure.
Yeah.
Other questions, please, from the audience?
I was
And
just
this-
wondering why the shape of the sample looked like a two, like there were two quantum two phase transitions. If you look at the shape of your sample.
Oh, I think it wasn't deliberately chosen for that. It was just, it happened to be one of the biggest single crystals that they had at the time, and we measured the sample a lot.
Well, then, in the spirit, if there are no other questions, Lucia, I want to, Ryan, you're going to ask one last
I have
question.
one more
can see, I
question.
can see
But
you
I don't
now
need to
physically.
hog all
Go
the
ahead, go ahead.
time.
Yeah.
So there aren't that many ytterbium-based superconductors. Do you have a favorite for another one to try? Or do you think, you know, what's next for ytterbium-based superconductors?
I don't think I have a really good idea there, because I think in general, it's just so hard to predict anything in the realm of unconventional superconductivity that I think as an experimentalist, I just need some data that points in some direction first.
Yeah,
So if
fair
I see
enough.
that, so I don't think I can answer that question right off the bat.
Okay, well, we'll just find some things to measure then. I'm done.
So I want to thank all the audience for coming to the spirit of the Magx presentations. We want to do it in this short, brief format. And also in my introduction, I said that Lucia brings creativity and a gregarious nature. I think both of those come through in her talk with her cartoons of her devices, and also with her cleverness of compromising watches. That I don't know how many more watches you have to go through, but
Oh, this one still works. It just
yeah,
needs readjusting
but also
every
then
once in a
to
while.
put it in your freezer and time-lapse photography. It's that creative energy that she brings to the team, and we appreciate it very much. Thank you, bravo, Lucia, fantastic.